Okay, so do communities and human activities influence any of these three factors? And if so, how? So we clearly do influence them. We don't influence the amount and distribution of precipitation in a drainage basin, or not necessarily, directly. We probably are doing so by the amount of heat that we are, inputting into the atmosphere. We're basically, or not the heat, but the greenhouse gases that later on cause re-radiation and then heat. They basically strengthen the evaporation and further condensation. So on a kind of far-fetched way, we do influence the amount of distribution of precipitation within a drainage basin, but more directly so, we influence the rate of precipitation infiltration into Earth. How do we do so? So you can think of any building that you might have to do, or any change in the farming style or anything. You are changing the overall topsoil that used to have been in that area. So say that you are constructing a house, the land that used to be previously, let's call it kind of sands and silts, is no longer sands and silts, but it's now concrete, and all the sands and silts that used to be where your house now is are elsewhere, probably within the drainage basin still. So we are changing the material and hence changing the infiltration of the water, or the capacity to infiltrate into the earth, either for the better or for the worse, or however you want to think about it. We are changing that potential. We're also changing how quickly that surface runoff reaches rivers. So by making different routes of the rivers themselves, sometimes we diverge the channel path. In mountains, actually, we do so very often. But also by placing different vegetation types, we what's it called? Plant a lot of trees in different areas. Those trees may be more likely to, divert the course of the path of the river itself. So it may take it longer or even shorter for a specific runoff place to reach the river itself. We may also diverge it based on the boulders that we place nearby, or the buildings that we place nearby. We might change that course, and hence how quickly the runoff at a specific location is going to reach the river overall. So you bet we do influence those three factors that in turn influence the potential for flooding. There are a few terms that we need to cover before we continue on about flooding. So the first one is going to be flood discharge. So remember that discharge, which is this formula right here, is going to be Q, which is discharge, equals the velocity times the area. Remember that formula. It's going to be in many quizzes, I'm sure, or exams. But the flood discharge itself is going to be the discharge of the stream at the point where water overflows the channel banks. So basically the amount of water that is flowing through when there's flooding. Nothing too fancy about that. The term that we need to know is stage. So the stage is going to be the height of water in the river above an arbitrary datum. For the most part, this arbitrary datum is going to be the bottom of the stream. So why do we use stage rather than discharge many times? So if you think of the formula for discharge, which is again velocity times area, that area is going to be the cross-sectional area of the stream. And if you think about taking the cross-sectional area at every point within the longitudinal profile of that stream, within the length of it, that's going to become pretty complicated. It's going to be a lot of calculating, because you literally have to go to each cross-sectional part of the stream and measure the length, the depth, and the width of every segment of that stream. So that's very complicated. So many times we just use a stage. You basically would get to the deepest part of the stream bed and stick a ruler up to the level of the water, which is a much easier measurement to make than the whole discharge. So that's going to be the stage for any one stream. The flood stage is going to be the elevation of water surface that is likely to cause damage to property. So it's going to be a hypothetical for the most part, where the water elevation above the stream bed is, so high that it's actually going to overflow the banks of the river. So once it does that, it's going to obviously be damaging to property. It's going to occupy certain parts of the floodplain, and it's, we have to do something about it. So that is going to be the flood stage, an elevation of that water in the stream that is now actually potentially damaging to property and to people. Okay, so a hydrograph is going to be a graph that shows you the changes in discharge and depth. So you have three different types of hydrograph as you are seeing here. I should say, you have one hydrograph that is based on discharge and time. That hydrograph is made through the use of a stage time graph and a stage discharge graph. So let's go about it this way. So discharge, as I said in the previous slide, I think, or a few slides ago, is very hard to calculate because you need to measure the whole cross-sectional area of the specific point at which you're taking the discharge. That can be very complicated and very long. So if you want to do it for all places in the river, it's going to take years for sure. However, the stage is an easier measurement to take. So at different locations where we have those gauges, is what they're called, we're going to be able to record both the discharge and the stage pretty accurately. And if you have enough measurements of discharge and stage for the same river at different locations, maybe you'll be able to get a relationship between the discharge and the stage. So if you were to measure the stage of the river at a location, but you don't have the discharge, based on the previous relationships that you've made from other records of the river, you'll be able to determine what the discharge is at that point. Again, just having measured the stage. So that is actually one of the things that many hydrologists do, is just check whether stage and discharge measurements should be, correlated at a specific point and at a specific measurement. Those are very important duties. They save a lot of time and a lot of money. So making good correlation between those two things is key, not just for river control, but also for flooding prevention. So definitely very important. So let's look at this hydrograph right here. It's showing us discharge and it's showing us time. There's another little box that they're showing us, which is this box. This is rainfall. So, and this other one is going to be the discharge through time. So here they're showing us that there is, let's say, 2 centimeters of rainfall, just to call it a number, that are falling within the first hour. Then let's say that there was 1.5 centimeters of rainfall for the next hour. And then finally, for the next hour, there was 1.75 centimeters of rainfall. They take the average of rainfall pretty much for that period of time. And then, as you're seeing the hydrograph, the discharge of those 3 or however many centimeters I said, what was it? 2 plus 1.5 plus 1.75, close to 5.25 centimeters of water that have rained throughout those 3 hours are expressed as a maximum discharge in the stream several hours later. So the time in between the rainfall event and the maximum discharge event at the stream is going to be called the lag time. So do you think that urbanization can affect that rate of discharge and stage of a river? Is it going to affect the lag time between the rain falling amount of water and the maximum discharge seen at the stream? I think so. So I'm going to give you a couple seconds to think about it. Okay, so what you're seeing here is that let's make this a kind of extreme scenario, but let's say that beforehand there used to be a stream that was vegetated all throughout from the mountains where it received most of its precipitation to the valley where the stream was the greatest. So Now there's a bunch of people moved over to where the stream used to be, and now we converted all that vegetation into asphalt. Let's make it extreme. So now those hill slopes through which the water used to flow throughout the vegetation are now flowing through just asphalt. So obviously the water is going to flow a lot faster through the asphalt than it would through the vegetation or vegetated areas. So you see that the lag time between that rainfall event and the maximum discharge that you would see is a lot smaller, and hence the flooding possibilities are a lot greater, are a lot faster. So that is one of the ways in which urbanization can affect that lag time, and hence that rate of discharge and the stage of the river. So another term is going to be the recurrence interval. So that's going to be the average time between flood events of a certain size. So as you're seeing down here on the diagram, this is the stream channel right there. This is even going to be the stream channel as you're seeing it, right? Okay, so that stream channel has a stage. The stage is going to fall right there, right? The elevation at which the water is above the bottom of, or an arbitrary datum, in which case I'm going to treat as the bottom of the stream. You're seeing here several lines on top of that channel. The first one is going to be called the stage and discharge of a 10-year flood. So that means that at that elevation, they're expecting the water to be every 10 years. There's going to be some sort of flood event every 10 years or so that in which the waters are going to reach that elevation. So that's going to be a mapped area for the 10-year flood. And that you can see both on this line in the cross-sectional view, and you can see it on the map line right there. It's going to be the darker grayed area. Okay. You're also seeing another line, which is the stage and discharge of the 50-year flood. So in that case, that line is going to be higher up because 50-year floods are less common than 10-year floods. You would need a bigger flood for the stage to be this high above, right? So they're not nearly as common. Remember that with natural disasters, for the most part, the higher the disaster, the less common it is. So again, for the 50-year flood, that line is going to be right there. That's going to be the stage at which the water elevation had to be in order for a 50-year flood to occur. It's also mapped here in a kind of lighter shade of gray. That's going to be the 50-year flood. And then the same thing for the 100-year flood, which would be, again, a flood of even greater magnitude to reach a stage of that elevation in order to cover the whole floodplain of this channel. So again, because it is going to be such a huge flood, it's not going to happen nearly as often. And so that is why it is a 100-year flood stage. Okay, so many insurance companies are actually after getting mapped areas for these 100-year flood events because people usually don't build in the 10-year flood or even the 50-year flood areas, but many homes and many buildings are actually on the 100-year flood areas of the floodplain. And so flood or insurance companies are after getting these mapped areas in order to be able to, get their clients to buy flood insurance for that specific reason. So government and insurance companies are both after getting these mapped areas solved.